So here's the situation. You get down at the edge of the table where your record player is, and you have put a little pin on your record so that you see the pin go back and forth as the record moves around. And so you just see it going from side to side. And it makes sense that it looks like it's going faster when it's right in the middle, and then it slows down coming to the edge, and then it goes the fastest in the middle, coming around again, and slows down at the edge. And that's what it looks like to you because you're only looking at the X component of the motion. But if we were to look down on this record player from above it, we would know that it's just going around in a circle. Now let's use this circle to figure out what is exactly the X component of the velocity at any time, or actually at any position. Alright, so the radius of the record is A, the amplitude, because that's the farthest on the x-axis that a pin could be from the center of the record. So we have maybe you're looking at this pin that's coming up out of the record. It looks like that to you. And at the position the pin is at right now, the x value looks to you to be only this great. So this is x. Because to you it looks like the pin is this far away on the x-axis. And we can just finish making this triangle, and it's a right triangle, and since we know two side lengths, we can use the Pythagorean theorem to figure out the third side length. And there it is. And that is one of our two similar triangles. Now here's the other one. We know that the overall velocity of the pin at the edge of the record player is tangent to the circle. So that's a really big velocity vector. But when you get down on the edge of the table, you're only looking at the x component of that velocity. So what that looks like to you is just the component of that velocity that is in the x direction. So let's call this Vx. Whereas the overall velocity that we drew before, let's call that Vmax. Because when the pin gets right up to the top here, the x component of the velocity will be equal to that overall velocity, that Vmax. So Vmax and Vx make up two sides of another right triangle, and here's the third side, and we don't care what that is because we don't need to use this side in our ratio. We can already make a ratio because we have two side lengths on this triangle and two side lengths on this triangle. And we know that these are similar triangles because this angle theta here is equal to this angle theta here. So now all we have to do is take the ratio of the side opposite of theta over the hypotenuse on the top triangle and set that ratio equal to the same ratio of side lengths on the bottom triangle. Here's the side opposite the theta over the hypotenuse. And after we do a little math, we can solve for Vx. And this equation should look exactly like the equation for the velocity of a spring in a simple harmonic oscillator. That means that if we took a spring and put it next to the record player and had it at its equilibrium position here and put some kind of mass on it, and then we pulled it to the edge of the record while the pin was at the edge of the record, and we let it go right as the pin came by, that spring would oscillate at the same rate as the pin, so that spring, the mass on the spring would always be directly over the pin on the record.